Hello everyone, I'm Suyong Lee from Computer Vision Lab in Seoul National University. The topic I will introduce is incorporating meta-learning for blind video super resolution. Here are the contents. First, I will briefly introduce the motivation and the contribution of the work. It includes blind super resolution, meta-learning, MAML, and the previous works that use meta-learning for blind super resolution. Then I will explain the proposed network DynaVSR and its results. Super resolution aims to generate the higher resolution output from the given low resolution input. It has been one of the popular low-level computer vision tasks for a long time. Recently, many deep learning-based super resolution networks have been proposed, but most of them assume that the error image is downsampled by a fixed known corner, such as MATLAB bicubic function. As mentioned before, previous works in super resolution usually assume a non-blind setting with a fixed bicubic corner. However, if a low-resolution image is generated using a different corner, the SR performance severely deteriorates. In the figure in the middle shows the super resolution result of non-ideal downscaled image, and EDSR, one of the good super resolution networks, returns an unsatisfying result. To cope with this problem, the blind SR methods are proposed. Blind SR is designed for super resolving the error image, even though we do not know the downsampling corner. It gives much better results than general SR algorithm in the real-world scenario, as shown in VSSR part. Blind SR is composed of two steps, the blur corner estimation and super resolution. In blur corner estimation, the blur corner for generating error image is estimated by an estimation network. Then the super resolution network for recording the estimated blur corner is trained. The figure in the middle shows the training and the test process of zero-shot super resolution, one of the blind super resolution methods. Assuming that the blur corner is estimated using the off-the-shelf method, the super low resolution image, SLR, is generated using that corner, and the super resolution network is trained using the SLR and LR pair. Then the network is fit for upsampling the image downscaling by that estimated blur corner. Applying the network to the error image will generate the final super resolved image. Existing blind SR methods run successfully using the combination of two modules, blur corner estimation and the SR network corresponding to that estimated blur corner. However, most of them run very slowly, since both modules require heavy optimization at test time. Let me first briefly explain the concept of meta-learning. Meta-learning aims to train a good meta-learner that makes a base learner adapt to different tasks at inference, while the standard supervised learning focuses on finding a single optimal model parameter that gives optimal performance for all tasks. Meta-learning aims to find the learning algorithm that fine-tunes a base learner to each task such that each fine-tuned model gives the optimal performance for that task. Recently, meta-learning techniques are beginning to be integrated into the many applications for test time adaptation. MAML is one of the ways to perform meta-learning, and the core idea is to learn a good initialization parameters for different tasks. Using the good initialization, the base parameters can be rapidly adapted to the new tasks. In addition, MAML algorithm is widely used for its generic model-agnostic property, which is also used in our work. As shown in the algorithm figure, MAML consists of two loops. The inner loop part is called learning process, and it calculates the loss using the support set of the task and gets the adapted parameter theta I prime. The outer loop is called meta-learning process. Using the updated parameters of inner loop, the loss is calculated again using the query set, and the base parameter is updated, as you can see in the red highlight. The updated base parameter provides better initialization, and it enables the fast adaptation at test phase. At testing phase, only the inner loop is used for adaptation. Using the support sets in test task, the parameter is adapted to fit the task same as inner loop process in training. Since the base parameter is well initialized, only a single gradient step update can make the parameter reach to the optimum from each task. There are a few existing works that incorporate method learning for super resolution. To use MAML for SR, we additionally need to prepare super low resolution SLR image, which is a further downscaled version of the LR input. When training, they can easily generate SLR images since they use known synthetic downsampling kernels. Then, training consists of inner and outer loops, where the baseline SLR network is adapted using the SLR and LR pairs in the inner loop, and the base parameters themselves are updated using the LR and HR pairs in the outer loop. At test time, they first estimate an SLR image from the given LR input image using the off-the-shelf blind kernel estimation network. Then, only the inner loop is active, and the final HR image is obtained by feeding the LR image to the adapted SR network. In this work, we propose a simple and efficient module to accelerate the kernel estimation process in videos. We call that as multi-frame downscaling network, MFDN in short. It is composed of 2D and 3D convolutions to effectively handle multiple frames. Putting the error video frame segments, the network finds out the blur kernel to generate error frames and generates the further downscaled version of them, called ISLR. Following the framework of MAML, the proposed method, DynaVSR, also has two loops. In the inner loop, we update both MFDN and the video SR network parameters. We first estimate the SLR frames using MFDN, called ISLR hat, and upscale it again to the LR scale using the VSR network. Then the calculated reconstruction loss is backpropagated using the both networks by calculating the error loss between ground truth, ILR, and the result of the VSR network, ILR hat. We also add an additional guidance to loss in SLR image domain to make sure that MFDN is estimating the correct SLR frames. The base parameters of MFDN and video SR network are updated in the outer loop. We use the same reconstruction loss function for both networks, but MFDN is updated using the SLR frames, while the VSR network is updated using the ground truth HR frame. For the experiment, we use various synthetic downscaling kernels to train the framework. We set the range of kernel as the combination of anisotropic Gaussian and the bicubic downsampling kernel. When training, the kernel is randomly sampled for every iteration to enable the model to adapt at various types of degradations. This is our full algorithm for training. The blue box shows the sampling of the frame segments for training the model. Each task consists of HR and LR and SLR images set using the randomly sampled blur kernel. Then the inner loop is conducted using the SLR and LR pair as shown in the green box. In the outer loop, orange box, the base MFDN and video SLR parameters are updated by the reconstruction loss and error loss at SLR and HR image domain, respectively. We show that the quantitative results for various Gaussian kernels, such as isotropic Gaussian, anisotropic Gaussian, and the mixed version. As shown in the table, DynaVSR shows the better performance compared to blind SISR method in most cases. Also, it can consistently improve the performance of 3 baseline video SR models by a significant margin on all evaluation benchmarks. To be specific, we compare the results with blind SISR method, since there are no standard blind video SR algorithms so far. Kernel GAN, KG in short, and correction filter, CF, are deep learning-based blind kernel estimation networks, and VSSR, DBPN, CARN are super resolution methods. IKC, which stands for Iterative Kernel Correction, performs kernel estimation and super-resolution in the same network. DynaVSR shows the best performance compared to blind SISR results, except IKC in isotropic Gaussian kernel settings. We attribute this phenomenon to the overfitting manner of IKC method in isotropic Gaussians. We also use 3 general video SR baselines and watch how much DynaVSR can improve. We found out that after using DynaVSR, the single-step iteration makes a huge performance boost for all cases. Moreover, note that the computation time for DynaVSR is significantly faster than the other existing blind SR approaches. Our blind kernel estimation process is 60 times faster than kernel GAN and 100 times faster than correction filter. Note that the processing time would be further decreased if we use more lightweight and faster VSR model. Qualitative results also demonstrate the superiority of the proposed framework. As shown in the figure, the blurry context of hill shown in the VSR baseline results gets much sharper using DynaVSR. Also, the network gives better results than the blind SISR methods. Even for real-world videos with no GT downscaling kernels are available, DynaVSR is still effective, although we only use synthetic training examples. This shows the generalization capability of DynaVSR framework to the videos in real degradation settings. To check the power of MFDN, we compare the SR results with other downscaling methods, BK21 downsampling, kernel GAN, and SFDN, which is a single image version of MFDN. The results table indicates that not only MFDN itself makes more accurate SLR frames than any other method, the SR results of VSR algorithm are better when jointly training VSR network with MFDN. To summarize the motivation and the contribution of our work, blind image polarization problem requires a downscaling kernel estimation process for each input image. However, existing work typically requires a lot of seconds for a single image, which makes it computationally infeasible for video applications. The proposed DynaVSR framework makes this process extremely faster by introducing an efficient multi-frame downscaling network, MFDN, and combining it with the baseline video SR model via meta learning and MAML. Also, it is generic and applicable to any deep learning-based video SR methods. Thank you for listening.